Hello everyone, and welcome to another educational presentation delivered via webcast, brought to you by the Storage Networking Industry Association, or SNIA as we like to call it. And today we're going to be talking about RAID on the CPU. My name is Paul Talbot, and I'm the General Manager for SNIA in the European region. And my role today is to act as a moderator for our two subject matter experts, Igor Konopko from Intel and Fausto Vaninetti from Cisco Systems. Hi Igor, how are you doing?
Hi, hello everyone. I'm doing fine, thanks.
Good, first time webcaster, so thank you. And Fausto, hi, hope you're with us as well.
Yes, thanks Paul for having me here, and good day everyone.
Excellent, thank you. Thanks to both of you for sharing your expertise today. So let me just start for the audience, just a few key points regarding the BrightTalk interface. There may be some of you that have not attended one of these before. Firstly, you can expand the screen size. It may be important because some of the screen details may appear difficult to read, so you can enlarge the screen. Importantly, you can ask questions along the way as well, and then depending on how much time we have at the end of the presentation, we may be able to get our experts to answer some of those questions, so please submit those along the way. A reminder that you can rate the presentation, so please don't forget to rate when we get to the end of the session. Please rate the presentation. A score of 1 means you'd rather have spent the time more wisely, but hopefully a score of 5 means it was a perfect topic for you. You can also, of course, send us your comments and your feedback on the general webcast program. All our contact details are on our website at snia.org. And finally, there is a PDF version of this presentation available for you in the attachment section. So let me start just by giving you a standard legal disclaimer from SNIA. The basis of this is really just to remind you that the material is copyright to SNIA and to detail the conditions under which we provide this material. And secondly, to state that we're not providing any form of legal advice here. We're not providing any warranties, either expressly or implied. And the content of this presentation, the use of the material, is entirely at your own risk. So just very quickly, anyone who is unaware of who we are a global not-for-profit association, and our job is to advance the adoption of all forms of storage technology. We have affiliated chapters around the world that provide that local representation, and this is why this webcast is being brought to you from the European region. Now, we use our vendor-neutral status to develop industry-wide standards, and we use our subject matter experts in our membership community to develop those standards, and then we provide the marketing and promotional programs that help aid the adoption of those technologies and those specifications and standards. As part of that, we provide an extensive range of educational materials on all forms of storage technology to help both the industry and the user to better understand how to implement and deploy that technology. And our educational materials kind of take a variety of different forms, but they include events and speaking opportunities, but also webcasts such as the one we're doing today. So without any further delay, that brings us to today's agenda, and I'm very pleased to hand you over to Fausto Vaninetti, who will guide you through the first section of our presentation today. Fausto?
Yes, Paul. Thank you. Absolutely. I see there is quite a crowd of people connected, so hopefully we will be in time to accommodate a few questions at the end. But let's start with an agenda, which is always a good way to start a presentation. The agenda we have prepared for you today is divided in 5 main sections. We will start by reviewing why NVMe SSDs are a great opportunity for state-of-the-art storage solutions, but they also come with their own challenges. Then we will do a recap of basic RAID concepts, and this will prove to be useful when we go deeper on how RAID on chip works. Like for every technology, it's also quite important to explore the main use cases, and we will do that. Finally, we will provide a glimpse into the future for this technology. So let's now get started. NVMe drives have recently gained lots of popularity. This is confirmed by storage and server vendors that are promoting their all NVMe storage arrays or hyperconvergent nodes. But what is the reason for this success? It's simple. The new interconnection protocol leads to better performance at a similar price point. Nobody can resist to this kind of value proposition. If we contrast and compare a more traditional SATA SSD to an NVMe SSD with similar capacity, two things emerge from the comparison. The price point is pretty much the same and cannot represent a key decision factor. But the performance is quite different. NVMe drives beat their old SATA counterpart by a factor of 2 to 6, depending if it's random or sequential I/O performance. As a result, it should come as no surprise that NVMe SSDs have surpassed SATA SAS drives in sales volume. And this actually happened last year. NVMe SSDs have a better performance, a similar price point, and allow for new compact form factors like M2 or E1. So everything looks good so far, but when you start scratching below the surface, some challenges also appear. So let's have a look inside a server. With traditional and well-established interconnect storage solutions like SATA, the SSD drives are controlled by a storage controller. This is typically a dedicated card that plugs into a proper connectivity slot of your server. The storage controller sits between the disk drive and the CPU. The purpose of the storage controller is to offer reliability, availability, and serviceability. The storage controller is the RAS delivery point. This is why you can do shameless insertion and removal of drives from your server. You can also activate location and status LEDs so that you quickly get to know the operational condition of a specific drive, or can identify a failed drive. But in the NVMe architecture, the NVMe SSDs plug directly onto the PCIe bus, just like you can see from this chart. And they are connected to the CPU. There is no dedicated storage controller in between. So how can we safely remove a drive without disturbing the CPU? Who will handle LEDs on the drive? Even worse.
Fausto, sorry to interrupt.
Yes.
Could you just speak up a little bit, please? We're just getting a few comments from the audience that you're hard to hear. So if you could do your best, please.
Yes, absolutely. I will try.
Thank you.
Even worse, let's consider data availability. In the traditional architecture, the storage controller can also implement RAID groups. In fact, it is often called the RAID controller. A RAID group is a combination of multiple drives whereby data are distributed in the group and protected. So, in case of a drive failure, we can still access our beloved data. But with the NVMe architecture, who is taking care of data availability? Who is in charge of RAID groups? How can I still read my data in case a single NVMe drive fails? Well, a until recently, the answer was simple, no way. And in fact, the lack of data availability with NVMe architectures has been a factor discouraging some customers from moving in this direction. And as expected, the industry started working on possible workarounds. But before we unveil the possible solutions and workarounds, let me clarify some concepts. We can classify RAID implementations according to this schema: hardware RAID, software RAID, and hybrid RAID. Hardware RAID is when we have a dedicated card for RAID support. Software RAID is when we let the operating system take care of data availability. And hybrid RAID is a mix of both. There is not a dedicated card serving RAID, but also we do not let it in the hands of the operating system. This table shows the differences among the three implementations when it comes to a variety of capabilities. Let me drive your attention on just two of them. With a hardware RAID implementation, you clearly need a dedicated card to add in your server. This is not needed when software RAID or hybrid RAID are used. When it comes to booting the operating system, we also see significant differences. With a software RAID implementation, we first need to have the operating system functional before RAID protection kicks in. In other words, we cannot use software RAID to boot the operating system. On the contrary, this would be possible for both hardware and hybrid RAID. So let's now summarize the possible options to achieve data protection with NVMe Drive. Of course, we can avoid using RAID altogether. Does that mean no data protection? Not necessarily. In fact, hyperconverged solutions do not use RAID at all. They use application-level protection under the name of replication factor or erasure coding. Then we have another option. We have the software RAID implementations. Linux has that with the Logical Volume Manager. Windows has an option as well. But remember, this can provide protection for your data, but cannot help in booting the operating system itself. The third option shown on this slide would be hardware RAID implementation. This is essentially the traditional approach, right? The difference is that now the storage controller has to be of a new type. It is called the tri-mode controller and supports SAS, SATA, and NVMe drives. This is an option, of course, but it requires you to purchase that card. You need to have a free slot in your server to plug it in, and it also adds latency between CPU and NVMe drives. The last option on the right of the chart is called RAID on CPU. This is what we are going to describe in more detail later. But let me summarize this new approach with a short statement. RAID on CPU is essentially having the CPU play the role of the storage controller. With this approach, no dedicated hardware is needed. Also, it supports data protection for both data drives and boot drives. As you can easily imagine, RAID on CPU technology is promoted and developed by CPU vendors. And to the best of my knowledge, both Intel and AMD offer their own specific implementation of that technology. Intel seems more focused on servers, whereas AMD has put out some descriptive document about desktops. And in order to be able to share the details on the RAID on CPU technology, in this presentation we decided to only cover the Intel VROC implementation. But before doing that, let's have a short recap of some basic RAID concepts. I expect them to be known to most people, of course, But I want to drive attention on something that is less known, such as the write penalty concept and the write hole challenge. This will come handy to better understand Intel VROC. So what is RAID? RAID is a rather old solution for data protection, so old that it even changed the name along the way. When it started, it was a solution to avoid using large and expensive disk drives and get some capacity by using multiple smaller and inexpensive disks. In fact, the original acronym meant redundant array of inexpensive disks. But then the focus changed from cost to data protection. And now the same acronym stands for redundant array of independent disks. So RAID technology offers the ability to read and write data to multiple disks as a single entity, increasing both performance and availability. There are multiple RAID levels defined. They can be identified by two parameters. K is the number of drives that carry data, and P is the number of drives that carry parity information. The parity information is used to reconstruct the data in case you experience a disk failure. The more parity info you have, the higher the tolerance to multiple drive failures. Of course, the implementation becomes cumbersome and less efficient in its use of storage space, so a compromise should always be found. RAID can also help with performance. In fact, it uses a striping technique so that read or write operations toward the individual disks can now happen in parallel rather than in series. Data striping in commercial implementations happens at the block level, not bit nor byte level. The most typical RAID implementations are RAID 0, RAID 1, RAID 5, and RAID 6, or maybe some combination of them. A full description of the different RAID implementations can be found in the SNIA disk drive format standard, referenced on this slide as a URL. And here are some examples. In simple terms, RAID 0 is called striping, and it offers no data protection. RAID 1 is known as mirroring, and it essentially writes the same data twice on two different disks. RAID 5 is data striping with distributed parity. It can protect from one disk failure. Instead, RAID 6 would protect you from two disk failures. When talking of RAID and RAID groups, it can be useful to have some clarity on terminology. We call a chunk the portion of data we write on a single disk. We call a stripe the sum of all chunks inside a RAID group. So the two parameters are linked together by the number of disks in the RAID group. The chunk size has implications on performance and storage efficiency. Some example. A large chunk size favors sequential access patterns, but it would lead to a waste of storage space for small IOs. The impact of chunk size on performance is more critical for RAID 5 and RAID 6 levels. Now, despite it is certainly possible to modify default values, my recommendation to all people listening would be to avoid doing that. When dealing with low-level implementations, there is always a chance to do more harm than good. So I would just trust the technology provider for having chosen the best compromise. And moving on next slide, I want to address one question that I often see when talking to storage administrators. The question is, what is the right RAID level I should use? Well, there is no easy answer here, or maybe the answer would be, it depends. Because the choice of the RAID level is clearly a compromise among several factors. For example, if you need data protection, you can discard RAID 0. If you need best performance, you may want to stay away from RAID 5 and RAID 6. Also, if all you have is a pair of disks, you will not be able to implement a RAID 5 solution. But of course, RAID 5 and RAID 6 offer a much higher storage efficiency as compared to RAID 1. In short, we can say that the choice of the best RAID level to use actually depends on the workload requirement. It's a compromise. When talking about RAID levels, I think we cannot avoid mentioning the write penalty effect. Essentially, when an application does a write I/O, the backend storage subsystem will have to execute multiple I/O operations, depending on the configured RAID level. This consideration applies to write only, not read. As you can guess, the write penalty affects more RAID 5 and RAID 6 because they are the more complex schema. I have a slide later trying to explain this in more detail. Now, I want to explicitly call out that modern disk arrays would not suffer from this effect. They implement several techniques, mainly caching, whereby the write penalty is hidden to applications. Nevertheless, the write penalty effect remains a critical one for RAID 5 cacherless implementations. So it's good to be aware of it. Now, this is the chart I pre-announced. Here, I'm trying to share the fundamental reason behind the write penalty effect. Let's consider a simplified RAID 5 implementation with 5 disks. 4 disks are used for data, and 1 disk is used for parity. When using the read, modify, write approach, we need 4 backend I/O operations when executing a single application write I/O. Why is that? As you can see, multiple steps are required to complete the application I/O. First, you need to read the old data chunk. Then you have to read the old parity chunk. And at this point, the magic happens, and the RAID 5 algorithm kicks in. This action all involves CPU and RAM. And so we can say it contributes to latency, but it doesn't affect the number of I/Os in the storage backend. When completed, you are ready to write the new chunk of data, and then you will finally write the new parity. So, in summary, the write penalty depends on the RAID schema adopted. For RAID 1, the write penalty would be a factor of 2. For RAID 5, like we as shown recently, it is a factor of 4. And I will not dwell more on the calculation example that is shown on this slide, because I want to cover another important and not well-known concept. And this concept is the RAID 5 write-hole challenge. Despite extremely rare, there is a possibility that when doing a RAID 5 write, you have a double failure situation. For example, one disk fails and power goes away. This is a double fault during the tiny time slot of a single write. As you can guess, very, very unlikely. However, it is possible. And the bad part of it is that it leads to silent data corruption. You will discover it only when you try to read your data again. This problem affects caseless RAID 5 solutions the most. When using a proper hardware RAID card, the issue is solved by using a battery or a supercapacitor on the card itself, so that the local RAM is always protected from accidental power loss. But a software RAID implementation cannot benefit from this, and more complex techniques have been proposed, like a distributed partial parity log or journaling. So now I think we have all the basics, and we are all set for getting into the weeds of Intel VROC. So Igor, let me turn it over to you.
Sure. Thanks, Fausto, for presenting your part. Okay, so right now I would like to focus in a little more details about one of the on-CPU RAID implementation made by Intel called VROC, or Virtual RAID on CPU. So RAID on CPU is really a hybrid solution which contains multiple components. CPU-related components, platform/UEFI related components, and some software components which works within the OS. And this is really what the VROC is all about. So as you can see on the slide, this approach contains two elements. One is the volume management device, which is embedded into the CPU, which provides you some of the features known previously from the HBA cards, especially the hot insertion and removal. Also, when we are doing this hot insertion and removal, it is very likely that some of the PCIe error can happen, and we would like to avoid to send these errors directly to the host. So this VMD layer provides also the error isolation. Yet another feature which the VMD provides is ability to manage your LED on your drive. This is something which was very known in a SATA or SAS timeframe when it was easy, but when the NVMe protocol was initially designed, there was no such a thing as a LED management. So hundreds of racks, and you need to identify your failing drive. You need to have this LED. So yeah, as I mentioned, the VMD is the part of the CPU, and it supports all the drives really. It behaves as kind of a virtual HBA card. We can call it also that way. What you only need is it has to be enabled by the vendors. So a compatible BIOS needs to be included in your platform, and proper drives needs to be provided to you. So VMD is also a baseline for the VROC solution. And VROC solution is really an enterprise class RAID solution which provides multiple RAID levels, boot support. It works in the Linux and Windows environment. And depends on the platform vendor, depends on the OEM. It can be licensed or can be embedded into your platform cost. It all depends on the OEM. Similar as with the support for different drive vendors. It also depends on the OEM how they handle this case. Okay, so let's move on to a little more details about the VMD. Some more details about the VROC and how it compares to the traditional RAID card. So really, in a case of the VROC, we've got these multiple VMD domains. Every domain can cover by 16 PCIe lanes. And so you can connect multiple drives to it. Typical NVMe drives got the by 4 uplink. So you can connect to every domain up to 4 drives at full speed. You can also, of course, connect more. Every CPU has 3 such of the domains. In case of the multiple socket system, you've got more of them, of course. And this is kind of a replacement for the traditional RAID card. Most of the traditional RAID cards are using by 8 PCIe uplink. Sorry, there is some noise. Okay, yeah, and you can also connect multiple drives to it, but always this by 8 PCIe uplink will be your bottleneck. Maybe not always, but very often in case of NVMe device. This was not an issue in case of the SATA or SAS drives, but in case of the NVMe, it is very often an issue, because if every of the drives can utilize by 4 PCIe uplink, by 8 PCIe uplink simply gives you only ability to fully utilize 2 drives behind such a card. Okay, so going on through the major feature of such a solution as RAID on CPU in our case, as I previously mentioned, this is an enterprise class RAID solution which uses the VMD for hot swap and LED management. It is a hybrid RAID. I saw in the meantime some questions from audience. What are the examples of the hybrid RAID? Yeah, this is the example of the hybrid RAID. What is important, it allows you to create both data volumes and boot volumes. Yeah, especially these boot volumes is a big difference in compare to most of the just software RAID solutions. We provide multiple RAID levels and also the ability to close the write hole, which Fausto describing that issue before. What is important, the performance looks really good with the solution. You don't need to additional separate hardware. You don't need the HBA card, and Linux and Windows, as I mentioned previously, is supported. For SXI, we only have a VMD part support. So all these features related to LED management, error isolation, hot plugs, they are available also under SXI, but not the right solution for now. Okay, yeah. So Fausto also presented you what are the typical RAID levels. With the VROC solutions, we support most of them. We support the RAID 0 with 2 or more drives, RAID 1 with 2 drives only, RAID 5 with 3 or more drives. You need at least 3 drives to make a RAID 5. This is part of the RAID logic there. And we also support nested RAID, RAID 10 with 4 drives. We can build a bootable RAID within a single domain, single VMD domain, or data RAID which can span VMD domains or even can span CPUs. I will show some more examples on the next slide. Chunk size, which Fausto also described to you, is configurable. For some of the RAID levels, we choose a different default chunk size than 128K, which is typically used to be default in a past, because especially for the RAID 5, the chunk size, the best or the most optimal chunk size depends on the number of drives too. So we are trying to do some recommendation in that topic. We also got a lot of different features which are known from the hardware card, so like ability to connect the spare drives, to configure the auto rebuild, expand the volume, migrate the volume type. So all the features, or most of the features known from the hardware card too. Plus the one additional feature which is also interesting is a matrix RAID. So if you, for example, have 2 drives, you can split your drives into 2 halves and use the one half to create, for example, RAID 0 and the other one to create RAID 1, for example. Okay, on a previous slide, I shortly talked about a little difference between the data RAID and the bootable RAID. So for the bootable RAID, there is a limitation that all the drives within a bootable volume needs to be a part of the same VMD domain within the same CPU socket. This is a limitation due to some Windows-related OS architecture, and so you can connect multiple drives. You can use a switches too, but it has to be within a single VMD domain. In case of the data RAID, if you don't want to boot from the particular volume, RAID volume, there is no such a limitation. You can create. We always suggest to create a RAID volume when all the drives are connected to the same CPU. Because this gives you the best performance. But there is also an ability to create a RAID which spans multiple CPU within a single platform, and as you can see in the middle of the screen. We also support PCIe switches, so if you don't have enough PCIe lanes, PCIe ports, you can use external switches and connect more drives. Of course, this can have some impact on your performance because there is a switching on the way, especially on the sequential-like workloads. But anyway, it's also a good solution if you don't have enough free PCIe lanes. The current limit is up to 48 drives in the whole system, and if we simply count the number of the PCIe lanes in every CPU, and we've got dual socket system, we can connect up to 24 drives direct touch, so without any switches with the full speed. This is the current platform limitation. Okay, Fausto also describes you this double fault protection. So the case when we've got both power loss and drive failure in the same time, and that we've got a different way of handling that situation. Initially, this was the issue for the software RAID, that they don't have such a reliable mechanism to close that one. With the hybrid RAID, we add such a features. We introduce it. So this solution is based on partial parity lock. It is OS dependent. In Linux, for now, it supports the distributed partial parity lock. In Windows, it supports both distributed partial parity lock and partial parity lock to put into the separate drive. So this is a technique which closes that right hole. But as always, there are some pros and cons. The main cons here is that it has some impact on performance. So by default, it is not enabled. But if someone is interested in the feature, this is fully tested, fully validated. Feel free to use it to enable it if it makes sense for your workload. When your workload it is important for your workload to have this scenario covered. Okay, I didn't told you yet about the way how the VROC can be configured. So there's different way to do that. Starting with the pre-OS environment, your BIOS menu. We've got a HII interface in this BIOS menu. This can look a little different, depends on the BIOS vendor, depends on the OEM, but this is the first place when you can create a RAID, when you can do all your configuration. Of course, if you want to create a bootable RAID, this would be the typical place when you can start creating your RAID before installing the OS. Also, when you are within the OS environment, you can, in Windows, you can use user interface, which is visible on one of the screens. You can also use the CLI. In case of the Linux, we've got also the CLI interface. Plus, there's a possibility to support some vendor management tools using, for example, RESTful API. So yeah, so these are the most typical way how people are configuring and managing the VROC for now. Okay, few words about the performance. So here we've got some numbers from both Linux and Windows environment. Performance is a little different in both of these environments due to the way how the drives are implemented. Generally, in most of the cases, it's scales very well. It scales close to the like a theoretical RAID model, especially on the right side. We are not seeing any significant bottlenecks on the right side, at least for the current drive generation, at least for most common configuration like 4 drives RAID with different RAID levels. In case of Linux, RAID also looks fine. The performance also scales pretty well. Not so good in Windows. In Windows, it scales up to some moment. As you can see on the slide, there is kind of some bottleneck when we reach around 1 million IOPS per single RAID volume, or totally 1.4 million IOPS for all the volumes in a particular system. There are some limitations for now, but anyway, this is still like 10 times higher than, or 15 times higher than just, for example, single SAS SSD drive. So these are still a very good numbers. Okay, practical use cases. Yeah. So right now, I believe I introduce you into the basics of the VROC virtual RAID on CPU. And now let's give me some examples where this solution fits best. These are of course not all the solutions, but some which came to our minds when we create the presentation. First one, of course, is the high availability boot. So I talked a lot about the boot support, yeah, and this is very common use case, especially in a RAID 1, so in a mirroring mode, when we want to ensure that even if one of the drives fails, then the system will be still able to boot, still will be able to operate. So this is a very common use case when we've got these two NVMe drives, and we used them in RAID 1 using VROC to boot, and we don't need to buy SATA RAID card or 3-mode RAID card, and yeah, this is the very popular case when we can reduce the total cost of ownership by not buying simply this hardware card. Another case when we believe this on CPU approach fits best is scalable RAID, scalable high capacity RAID. So this is the solution when we've got really a lot of drives. We want to create a high capacity RAID. In case of the traditional RAID cards, we've got this, as I mentioned, this limitation. Typically, the whole workload to and from HBA card was transmitted through by 8 PCIe lanes. For NVMe, this was off, and this is a serious limitation. So when someone wants to create such a big RAID, which could make 20, 40 drives, it has two options in case of traditional RAID cards. Either put all the device behind a single RAID card and be limited by this PCIe, or buy a multiple card. But then if you buy multiple cards, you cannot create a RAID which spans these cards in most of the cases. So there are pros and cons of the both solutions. In case of the on CPU RAID, there is no such a limitation, as I showed you on the previous slide. For the data RAID, data volumes, you are not limited to particular domains or to particular CPU, so you can scale it simply. You can scale it as you want. Okay, so these were two use cases which I believe it was worth to mention about. Right now, I would like to shortly talk about what's next with some examples of our preliminary data about one of the way how such a solution can be extended in the future. And it is the way how we would like to proceed with that solution, how we would like to extend this solution, is to add some integrated caching into it. In case of the HBA cards, there were a DRAM, power protected DRAM on the card, which was used as a cache for RAID, in order to, of course, improve the performance. Here we don't have such a ability to use a power protected DRAM, because DRAM in the platform is not power protected, of course. So we came out with a different solution with using faster drives, for example, Optane drives, as this acceleration layer for slower drives, either for the NVMe NAND drives or even for SATA SSD drives. The solution right now is Linux only, but as the whole VROC product is fully validated, we provide this enterprise-like class of the whole solution. Yeah, and as I mentioned, there are multiple ways to use that feature. What is important because many customers are scared to just use a single drive as a cache, we can use the VROC RAID 1 as a cache. So just connect two drives, RAID them together, and use that as a cache. So we don't have this single point of failure which customers would like to avoid. What is even more interesting, that this caching it's not like a dummy, it's not a dummy cache. It allows you to specify some particular rules to improve the most critical elements which are responsible for your server performance. So overall bandwidth of the storage, latency of the application, and also the endurance, because this is the element about which a lot of people are forgetting about, the whole system endurance. This is also very important. And in order to achieve that, the caching engine allows to create kind of a roles, kind of a classes of the particular files, particular IO sizes, particular directories, which describes somehow your workload. So you can specify only some subset of the data which should be cached. And based on our experience, there are some groups of the data which always should be cached. Maybe not always, but in most of the cases should be cached. The first one of them is the data which are very often invalidated. So this helps you to improve your a backend storage endurance by moving this data to some other media which has the higher endurance. So we are simply not overwriting the data on the backend so often. And also these are the first two groups of the data which we typically suggest to put on such a caching solution. The last one is about of course the hot data which are accessed often. This is known from ages, for any caching solution. But these two first bullets, this about the invalidated often with the short lifetime or overwritten frequently data. This is the something here. And here are some examples of the solutions which we tested. That this is the MySQL example where went to the array of the NVMe NAND drives. We add Optane drives by properly configuring the cache policy. This is something what I talked about. In that case, we are caching everything but database blocks. So we are caching every IOs which the IO size is not equal to the 16K, because this is the size this is the access pattern of the MySQL to the database blocks. And as you can see, we are seeing some very, very nice performance, latency improvements, also increasing the endurance. Yeah, so this is an example of the solution when even NVMe NAND drives can be accelerated by using something faster, something with higher endurance. Next solution, this is another proof point. This is the MongoDB, so another database. Here we've got a little different solution, because instead of accelerating the NVMe NAND drives, we are accelerating the SATA SSD, SATA NAND drives by also adding this caching layer. And here we've got a little different policy. We are specifying the policy based on the particular files in this Mongo database, especially like journals and other temporary files. And as you can see, we can also improve the performance, reduce the latency, and increase the endurance. And by the endurance, we are simply calculating how many your transactions or operation you can execute on the particular drive through the whole lifetime of your platform. Yeah, we're just comparing these numbers for the both solutions. Okay, so yeah, that was the last slide from my side about the on CPU implementation from Intel. So thank you everyone, and I believe right now Paul is.
Thank you, Igor, and thanks also to Fausto. So guys, we've got just short of 10 minutes, and I'd like to use the remaining time to get through some of the questions. We've got a whole bunch of questions from the audience. So what I might do is try and pick some that hopefully Igor and Fausto you can give very short answers to, so that we can get through as many as we can. Igor, may I start with you? There's a lot of questions about, does VROC require platinum processors, or does gold and silver processors also support VROC?
So it is not. It is also supported on a silver and gold version. It does not require a platinum version, at least from the CPU perspective.
Okay, good. Is there a difference in performance between the processor categories, platinum, gold, and silver? Do they all have the same benefits?
There always can be because the silver, gold, and platinum the processors got a little different performance, overall performance. So it might impact your whole solution. It should not have a very significant impact on some like a synthetic benchmark like FIO or IOMeter, but from the whole system perspective, it can be a difference. For example, MySQL use a lot of CPU cycles, so then if you choose silver instead of platinum, for example, you can be limited on other layers. But just on a VROC layer, it shouldn't be a noticeable difference.
Okay. The simple question now, where can I learn more about the VROC IC option? Presumably you've got pages on your website, have you, Igor?
So soon there should be more materials available online about this solution, and also I suggest to contact your OEMs who you're buying all your platforms from. These people are typically also a good contacting point about any type of VROC integration or implementation on the particular platforms.
Okay, thank you. Great. Next question. Does this VROC need separate OS drivers, or do they have in-box support for both Linux and Windows?
So for Windows, it requires out-of-box drivers. For Linux, that part of the VROC solution is in-box, but depends on the particular kernel version and distribution. Sometimes also some out-of-the-box components are required. It really depends on the kernel version and distribution.
Okay, great, thank you. I'll just keep these going if I may. Is Intel VMD present on all Intel CPUs by default? So
it is available. Here I was talking from the enterprise server perspective. So it is available on all the current Xeon CPUs.
But let me add something to this, Paul. Let me add something to this question, because I've seen several that are going in the direction of practical implementations, vendors that support VMD, VROC, or both, and so on. So let me try to summarize the multiple questions I've seen, just adding some content here. So Number one, the fact that a CPU supports a functionality does not mean that the server incorporating that CPU will support the same functionality. So, for example, there is a question about the number of PCI Express lanes that are supported by Intel CPUs for VROC. And I think the question is not really the proper one, because even if Intel would support all PCI Express lanes for VROC, which is, by the way, this is what they do, this does not mean you can use all of them for VROC in your server, because you also need to consider that between the CPU and the SSD and NVMe drives, there is a motherboard in between. So you need to make sure that the motherboard was designed in order to be able to leverage all those PCIe lanes for support of VROC, which is not often the case. I would say that typically only 50% or maybe even less of the PCIe lanes on the CPU can be really used for VROC in commercial, in server implementations. Another point, VMD and VROC, are they available on every server? Well, no, but majority of server vendors are clearly trying to support this kind of technology. But there are differences. And I think that the main difference I've seen out there in the market comes down to the way you implement the solution. Because we didn't explicitly talk about that, because it was intended to be a technical presentation about the technology. But just be aware that in principle, Intel VROC is a licensed feature. So you would need to pay a license to enable it on your server. And the way it was implemented by some vendors is that when you purchase a license, you get a hardware dongle that you would plug into a specific slot in your server. And that would be the proof point that you paid the license, and then you can use the VROC capability. Now, other vendors, my company, for example, has decided to take this route. Other vendors have incorporated and absorbed the license into their own firmware. So if you buy a UCS, for example, you don't need to pay for a license to use VROC, because we are already paying that for you, essentially. And you don't need hardware dongle to plug into the motherboard. We have incorporated the key, the license, into our own firmware. So it's a very nice implementation. But this is just to say, you cannot just look at the CPU. The CPU can support multiple things, but does that imply your server is able to support all those capabilities? No. You need to look at the motherboard, the design, the firmware, and so on. There are many more details that will need to be discussed in order to make a proper assessment.
Okay, Fausto, thank you. We're almost out of time, and we've got so many questions, but I think you addressed a number of them there. For those of you that we have not got to your question, my apologies. What we will do is capture all of these questions and do a FAQ on our blog. So we'll post something in the next few days when I get the guys to answer the questions. So they'll be available to you. So in terms of wrapping this up, first of all, thank you to Fausto and Igor for your expertise. I think a lot of people seem to have appreciated this presentation. So please don't forget to rate the presentation and let us have your feedback as you sign off. And that basically concludes the presentation for today. Thank you to all of you who joined the webcast. We hope you enjoyed it. And please look forward to many more SNIA presentations on storage technology as we go forwards. So again, Fausto and Igor, thank you for your time today. And thank you to the audience for being part of our presentation today. Thank you very much.
Thank you.
Thank you.
Goodbye, guys.
Bye.